Okay, good morning everyone. So I'm Keith Anderson. I'm the Subsea and Export Systems Manager with Wood, and I'll maybe today it's about giving a bit of a background to floating offshore wind, perhaps why we go there and what some of the challenges are around that. But I'll give you a little bit of a background of a couple of slides at the start just about Wood. It won't take long on that, and we'll go then into the offshore wind side quite quickly. My background myself, I'm an ex-civil engineer, and then I've spent almost 19 years in the oil and gas industry. Through that I've evolved into the renewable industry as well, because a lot of the things, and you'll see some of it as we go through, particularly when you take it offshore into the water, there's a lot of similarities in what we do in offshore engineering with what we need to do for offshore renewables as well. We're looking at things in the water, things on the seabed, and that's all similar types of technologies, and we'll chat a little bit about that. But I was asked a question earlier about what do you think of of the renewable industry for the northeast. I think once you start getting wet with it, it really does tie in with sort of real knowledge and domain disciplines in the North Sea that we have. So it's a really good lead into some of these. If you took the turbine off the top left picture there and put a process unit on top, that just looked like a normal offshore production platform. So there's a lot of similarities. So. Don't know what that was there, sorry. Bit of a beep. That's better. Okay, so just as a bit of background on the company as well, because Wood's pretty well known in the northeast here as Wood Group in the past, and was seen as an oil and gas company. We're something like 6% non-oil and gas now, so it's moved quite a lot, but it's sometimes hard to bring people along in this area that actually the company's evolved and is different. We've got about 55,000 people across 60 countries and 400 offices. We've put in over 160 gigawatts of renewable energy we've been involved with across the globe. So there's a fantastic background we have. We've got quite a large footprint across the globe, as you can see there, and covering sort of multiple industrial sectors. So oil and gas was one of them, but it's across all of the sort of energy and utility sectors for power generation, for manufacturing, for chemical industry, and for automation. So pretty much a multidisciplinary consultancy now. But the key one we want to talk about today is the clean energy and where that clean energy is with respect to offshore wind and predominantly floating offshore wind, which I think we'll come to is a really interesting one for your learning here, because the northeast Scotland is where we've got the key demonstration sites at the minute. And we've got Pilot out there, and we've got Kincardine, and you can see from the coastline here. So, something that brings it into something being real. But our clean energy service line, we work across all stages, from very initial advisory services, talking to the banks and the lenders about trying to bring the money across the line for these developments, through to the concept engineering, the detailed engineering, and then through into execution and operation. So Wood also operates a number of wind farms as well. So we have full operations and maintenance side of that. So as well as doing the engineering and concept work up front, we then work through the engineering, the construction management, and we actually then operate them. What we don't do is supply products, so we don't provide turbines. We're not the pipe mill that's going to come out with the towers either, but what we do is the construction support all the way through that. So I'm not going to talk any more about Wood. It's not about a sales presentation on the company, but also we've got to put something up there just saying background, where we're from, why we're in a position to talk about this. And I think hopefully as I go through this you'll see some of the knowledge that we have in this domain. So on to the real part of what we're talking today. Right, we'll talk about floating offshore wind. I've talked a wee bit, shown a couple of pictures, you might not be familiar with it, so we'll talk a bit more about that. We'll go through what the actual offshore wind market is. What is the technologies that we have to look at with that? And then how do we assess these? How do we know they're going to be suitable for use? How do we design the infrastructure that goes out there? And then just a little bit of a summary about where we are with that. One thing I meant to say at the start, typical Scot, I can talk way too fast in an accent no one can understand at times. So at any point, feel free to ask me to slow down or to repeat myself. And any questions going through this, fine, just ask as you go. If I feel we're getting bogged down in something, we'll stop and move on, and we can address it again at the end. There'll be plenty of time for any questions towards the end again. But please just shout out as I go through this, okay? So So I guess the first thing is why even consider going offshore? It's a real pain, isn't it? Because for an onshore wind farm, it's easy. You can take your cement trucks in, you can bring your cranes in, you can build it all. If someone needs to go and do operations on it, they can walk to work. You know, doing things onshore is just so much easier, so much better, isn't it? Why have we gone offshore? Well, it's the availability of land is one of the things. It's the impact to society, and that's societal norms. There is pushback. There's a lot of NIMBYism. Not my backyard. You know, trying to get the planning and the consents through. Certainly in the UK, they're all on top of hills because that's where we get the greatest energy resource, and that's a challenge because then they're visible. So we have issues with actually being able to develop wind farms onshore. And also we've got lower average wind speeds onshore because you get a lot of friction with the ground and the topography as well. So if we can take our wind farm offshore, we can reduce some of the impact on society and some of the planning requirements there. You know, there's less objections once it's over the horizon or it's out in the water. And we actually have much more resource there. There's a lot more sea area than there is land area, and we've generally got higher wind speeds the further offshore we go. So I guess further offshore we go, sort of the deeper the water we go as well. But we tend to have higher wind speeds than we do on land. So there's a lot of things that drive us there. So despite the challenges in cost for the construction and operations, the fact that we can actually get out there, have bigger turbines, have them through the planning a lot smoother, and there's greater wind out there, that's all the bonuses for us. But it is a challenge with our accessibility. As I say, you can't just walk to work, and you're very much at the mercy then of the elements. And strong winds, high waves, you can't access your platform. So if you had to shut in a platform for a given reason, or a turbine, you cannot necessarily get out there to intervene in it. And that can be a challenge because quite a number of these have been daisy-chained one turbine to another. And if the one closest to the offshore substation has a failure in the electrical system, it can shut the whole wind farm down until you're able to go out. So you don't have those sorts of downtimes onshore unless you get lots of deep snow, but tend to be you can get through the wind and the rain with a 4x4 wherever you need to go. It's not the same offshore, so that is a challenge for us. The other challenge is as we go into deeper and deeper water. Most wind farms out there just now are in pretty shallow water, and they're developed with single monopiles, and we'll talk about what they are. The deeper we go, we then have to start fabricating more and more complicated foundations. And then we get to a stage where it's just not going to be economic to keep building foundations from the seabed. So there's a challenge with where we can go in deeper water, particularly if we stay fixed. Okay, that's actually a picture of the Beatrice demonstrator. So we've now got the Beatrice wind farm out there. But the Beatrice demonstrator is something that we engineered a long time ago now as wood. And what you can see in the background is oil and gas platform Beatrice that this is associated with. And we operated it after the construction from that platform as well. And what that did is that proved technology. That's a jacket structure. That helped to prove the technology and having it in slightly deeper water. And then, obviously, you'll be aware, we've had now the large Beatrice developments been finalised offshore now. And that's all come from having two turbines next to an oil and gas platform once upon a time, taking us out into that sort of water depth. So it's a bit of a link up there again. So that was operated by people from the oil and gas industry at that point, because it's quite handy when people are there. It's easy just to come over on the boat to see that one rather than coming from shore. So there's a little bit of hand in hand between the industries there as well. So fixed offshore wind. Offshore wind's nothing new. We're decommissioning offshore wind now. It's been out there that long, some of it. It just seems new because it's getting more and more attention in the media. Offshore wind's not new. It's been out there a couple of decades. Even in Scotland, the oldest ones, the Robin Rigg ones off the west coast of Scotland actually. But the knowledge there, the foundation has said monopiles. Monopile's just a single big tubular that's driven into the seabed, yeah? And then we put the wind turbine tower just rests on top of that. As you start going beyond about 30 metres water depth, those become a bit of a challenge because you've just got one single tubular coming up. It becomes quite prone to movement and sway and the loads within that. So as we go into deeper water, what you see there's the jackets from Beatrice, the ones fabricated down at Bifab. Beatrice is, I think the deepest there is just shy of 80 metres water depth or thereabouts. You know, but we have to go to a different type of foundation for the fixed offshore wind in the deeper water. A single turbine is quite a simple, a single monopile is quite a simple thing to fabricate. It's not that much steel in it, it is just a tube. The minute we have to go into the deeper water and look at jackets, then the cost starts going up fairly exponentially, really. You know, that's very much an engineered structure, and the fabrication's a lot of members in there, a lot of tubulars welded together. It's a big thing to transport out there as well. You know, you can get dozens of monopiles onto a vessel. You can't get dozens of these onto a vessel, so suddenly your costs are starting to go up as you go into deeper water. And from the Carbon Trust Technology Review, you know, their take on this is that floating wind's nowhere in shallow water, but as you start going beyond 50 metres water depth, then you start to be looking towards a competitive nature of floating versus fixed. I think that personally is a little bit ambitious. I think floating still wasn't on a par with Beatrice in about 80 at the minute, but as technology changes it may well become that. But certainly you wouldn't be going much deeper than Beatrice, I think, before you really having to be considering moving to floating wind. And what's of interest is, given what the Carbon Trust are saying as they look to the future, Europe's wind resources generally, water depths where floating is going to be the most commercial one if we get that far to generate it. The other thing I would say is, in its side as well, with fixed offshore wind, we've got turbines now over and above 8 megawatts. I think the largest one in Aberdeen there, the Offshore Wind Development Centre, the big ones you see off the end of the beach, is 8.8 megawatts, which is phenomenal size turbines. They don't look particularly big, but they're a long way offshore. They just seem as if they're close in and small, because what you see onshore, offshore turbines are massively different in scale. And actually, the height of that's the same height as the new Forth Road Bridge, the Queen Elizabeth Bridge at Edinburgh. You know, the pillars on that are the same. It's the same height. You can actually Google that up quite easily if you look up Vattenfall EOWDC for the development centre, and you'll see that. So these are massive turbines that we have there. So it's
those turbines on the beach, are they floating turbines?
No, they're all fixed in different foundations. That's a test centre.
What is the water depth?
I don't think it's particularly deep out there. I think it's 30-40 metres. I can't quite recall.
What about the structure diameter?
Well, there's some of them are monopile, some of them are jackets, because they've gone for some that are piled, some that have got suction bases, because it's a test centre. So it's not. It is nominally commercial, but it's actually what they've gone for. So they're testing 66 kilovolt cables back to the structures as well. Generally, it's been 33 kilovolt cables. So they're testing the high voltages. They've gone for the larger turbines. And they've got multiple different foundations. The diameter of the towers, I actually don't know but the heights, whatever height is the bridge down over the Forth at Edinburgh. So very, very, very tall. So sometimes hard to get that when you see them from the beach, because they're actually several kilometres offshore. They're not just a little bit out. It's about 6 miles out, I think, actually. So fixed offshore wind, it exists. We've got big turbines there. It's quite a mature market, but we've got a limitation going to deep water.
Yeah. Do you have any picture drawing to the detailed specification of foundation for fixed and floating wind turbine?
Do I have?
Detailed.
Okay.
So
Yeah. Okay. Well, I don't have. I'm not got any details specifically of that. Floating's different because it doesn't touch the seabed, and we'll touch on that. But fixed, if this is a pile, this is a tubular. That is then driven into the seabed. It's a pile, by one of any other means. It's a pile that's driven into the seabed. Okay, so it could be 6 meters in diameter, very big piles, driven down into the seabed, and then there's an interface. So the pile sticks up to here, and then what you do is you come out and you lift your turbine tower and you drop it on top. For these here, these ones here, well, depends, can be small pin piles for the foundations to put that jacket onto the seabed, or what's called suction cans, which are big diameter, very short length piles in a way. But what you do with them is once they're on the seabed, you suck the water out the top and that dries them down into the soil. So But that's basically, it's a gravity base or a pile base that we have amongst that. Okay.
So, the deepest possible for seabed is 60 meters?
No, you could make one 160 if you wanted, but it wouldn't be economic. There's no technical limitation, it becomes economic. Well, I'll say there's no technical, but certainly in the North Sea there wouldn't be any tech. We've got fixed platforms in 150, 160 metres of water depth for oil and gas, so we know we can do it, but it becomes uneconomic, and we'll talk about that a little bit later on. 'Cause the difference here, if we go to floating offshore wind then, and we look at that, is that we don't have anything contacting the seabed. It's all floating. The turbine itself doesn't touch the seabed. So what we have to then put on that is mooring lines, so anchor chains that come down off of that. So you'll see we've got the moorings here coming down onto the seabed, and they will come down to an anchor. Now that could be a pile or a big anchor, like almost like you see on the ships. There'll be different anchoring styles down on the seabed. So.
Regarding location, how do you have a permit system on what area to use or not?
Yeah, I mean that's a whole different topic in its own right.
Yeah.
But consenting and permitting for these, yes. Generally, within the 12-mile limit where we've got all the fixed offshore wind, generally it's the Crown Estate are the owner of the land, and you have to apply for your permits and your consents, and you have to get the regulatory approvals. You need all that then before you can actually bid to actually construct something. Because in the UK sector, for instance, it's done through, has been done through contract for difference, and effectively you bid what you think the subsidy you need is, and the person with the lowest subsidy will win that round, but only if they've got sufficient early engineering done to consent. Now that consent, as you can go and you can look some of that up for the Firth of Forth, for instance, very, very difficult to get because of bird populations, and the RSPB had objected to that for a number of years. So it depends where you are. There's the mammalian life, what's on the seafloor, sort of benthic lifestyle, life organisms as well. There's a whole bunch of things will actually come into that. You also need to be somewhere where you've actually got access to a grid connection, otherwise there's no point putting in a wind farm, you can't bring it back. So there's a range of things there, but not really something I've prepared to talk about in here. I'm really talking about the technology more than some of the planning behind that. So in a floating system, we're decoupled from the seabed. We're not touching the seabed, so it's effectively independent of water depth. So we've got these mooring lines. They give us station keeping so we don't drift around the rest of the North Sea. And then what we have to have is our power cables then coming off are going to be a dynamic system. They're going to move. So generally in fixed wind, the power cable's pretty static because the turbine's not moving and the seabed's not moving. Now we've got something that's going to be moving around, that we have to have dynamic cables. Well, actually, again, that becomes a direct transfer from the oil and gas industry as well. All of our floating production systems in the North Sea have dynamic risers and cables connected to them. So again, it's technology we bring across, but it's another level of complexity, and we'll talk about some of the challenges with that as well. So it's a step out of technology we developed to go into floating wind. What will limit the water depth really will be the weight that hangs off of the hull, and that weight comes from the mooring system and the cables, and the deeper we go, the more weight on the cables, the more weight on the mooring system being added to the hull, so the bigger the hull needs to be. So you could put one out there in 3,000 metres water depth, but it's going to be a lot more expensive than one that goes in 300 or 100 metres water depth. But to all intents and purposes, they are independent of water depth, but no one's looking at them in massive deep water as yet like that, because you've got to tie it back somewhere. So you want it to be next to population centres. So just a little bit of the terminology. So what we have is we've got the turbine tower here, obviously the blades. Then where the generator and all the blades, hubs, and that is, that's called the rotor nacelle. Yeah. And that area there is very much, that's quite a narrow market. People like Siemens and that providing the turbines and the nacelles. But the tower's just dumb steel fabricated anywhere. And then the hulls, there's many different types of hulls. We'll come to them. Some are concrete, some are steel. But you know, relatively straightforward systems, power cables, and then the mooring systems there. Okay. But unlike fixed wind, this is quite an immature technology at the minute. Yeah, there's a lot of global demonstrator sites that have been up and running, of France, of Portugal, UK, of Japan, and we've got to a stage where there's no settled technology. I guess we're all quite familiar with wind turbines with 3 blades, you know. That's because we've sort of settled on that. But early industry looked at 2 blades, 5 blades, different things. A bit like tidal just now are looking at, is it 2 blades, is it more than 2 blades, are they more like fans, are they ducted, are they not? You know, we've got to a stage where the turbine in sort of wind is sort of settled. There's a few innovative things out there about having horizontal axis and vertical axis blades, that type of thing. But to all intents and purposes, that's a settled technology. But the hulls aren't. And there's a range of different hull types. So you've seen at the very first page there, I had what we would call a semi-submersible style. Then the page before this, it was what we'd call a spar hull. We'll come back to, I've got a slide with all of them on it. This is a different one yet again from floating power plant who are developing these. And they've actually got, they call it a floating power plant rather than floating wind, because in here they've also got wave energy converters within there. And their whole idea of this, with the bit coming out the back, is this weather vane's round, there's always an area in the lee at the back, so there's less waves at the back of it, so that vessels can come in for maintenance. So where they might not get access to other types of turbine, this one, because it's got a bit here that acts a bit like a mini harbour offshore, they should be able to get in maybe more aggressive conditions. That's their USP, their unique selling point that they're trying to put to the market. So there's quite a lot of different, and also integrating the wave energy converter to it. So there's a breadth of things there, and there's no clear way yet for the industry forward, hence all these demonstrator sites that we have. Turbines aren't quite as big, so I think the biggest out there floating just now is on a 6 megawatt. So still quite large, but not 8 or 8.8, and not where fixed is going. So you'd need more of these than you would of fixed ones to get the same power. Yeah, it's quite a straightforward thing. The understanding of the dynamic forces on the turbine and the hull, we're used to aero-elastic loading, we're used to hydrodynamic loading, so loads from the air, loads from the water. But we've not really had systems out there where there's been massive loading from both, and trying to come up with algorithms and methodologies to actually understand that combined loading on something that reacts to both the air and the water. Ships have got a big windage area, that's fine, that's quite a simple calculation. This is different with the rotating blades and the loadings coming into that, depending on how we feather the blades, etc., etc. It becomes a much more complicated solution, and that's something the EIA have got an international project running on to help characterise and take forward that. So that's an area where we don't have full domain knowledge yet as an industry. But there's a lot of good stuff happening in this region and in this area, and we've got the Statoil's Highwind development that's sort of offshore Aberdeenshire offshore. It's in the Buchan Deep. Their spars are very tall structures, and I've got an installation picture for that later on. But that's the first ever multiple floating turbine setup that's out there. So there's been a number of individual turbines tested to see they're working. Now trying to see how an array works, putting multiple ones out there with the connections of the cables and everything else, and see how that moves forward. So that's the next big step for floating wind at the minute, and it's happening here. Excuse me. Just waiting to sneeze. It'll come in a minute. Kincardine Offshore Wind Limited as well. So Cowell, their demonstrator went out last September. Just off, you can actually see it from the cliffs in Aberdeen. If you go just sort of south of the town, you can see it, and certainly you can see it from Stonehaven and Newton Hill. You see it from the Joe Carriageway south. Actually, there's a floating turbine just sitting out there as well. And that's a really interesting one, because that one ties back into the small substation in Altons in Aberdeen, and that substation is also then directly connected adjacent to a hydrogen fuel facility. So you can almost see the whole clean energy cycle there. can you, of where we're aiming to get to as an industry? Because there's a bus fleet in Aberdeen that's driven by hydrogen. So whether it was originally set up, I don't think it was as clever as that, but it's actually a really good demonstrator that the guys managed to join it all up at the same location. So we're generating intermittent clean energy. We can use that, we can store that within hydrogen, and that hydrogen is then used to give transportation. So you can really see that whole green cycle occurring there as well. And hydrogen is one of the key options for wind in all different ways, that between that and battery storage, isn't it? But you'll know more than I do going through the renewable course on that. But how do we store renewable or intermittent renewable energy? And that's the two sort of key technologies vying at the minute. So that's a really interesting one, the cowl. So as I say, you can see it. It's with the naked eye. Certainly on a sunny day, it sort of glows a wee bit as well. So I think that's great stuff. Again, I was asked about the northeast, so there's a couple of real key things in this particular area that's happening in. Hi.
Would you say that it kind of hasn't moved past demonstrator sites because of the limited size of the turbine? Because
Yeah.
I suppose only when you're going further offshore deep waters to get higher wind speeds and therefore more power. So would it really be when we're starting to get kind of 10, 12 megawatt floating turbines that you'll see more of these?
Yeah, I mean, I think if you look at the 6 megawatts that's available there, it's a lot bigger than quite a lot of the fixed wind that's been out there for a number of years. There may be a little bit in that, but it's people haven't had to go into deeper water. And in fact, the UK doesn't need to. We've got so much that's still achievable, and a lot of Europe doesn't need to. We've got so much that's actually achievable. Although 80% of it's in deeper water, that 20% is still nowhere near of existing resource, still hasn't been targeted. And it's been what's been the drive behind it. And you cannot come up with new technologies without subsidies. It's exactly the same with Wave Energy Scotland that are set up to actually develop wave energy in Scotland, and they put money into projects. Tidal's really had a real challenge when the subsidy model changed, because there's not the backing for these technologies until they can see the revenue stream, and that's not going to come until you've got a couple of them that are proven and capable. And it's starting to get there. Many people are buying into a lot of these types of technology now. Shell bought into Stysdal, Aker bought in with Principal Power, and the list goes on. Starting to move these forward. But without having some track record, you cannot get finance. If you cannot get finance, you cannot do the development. And that's where the challenge is at the minute. And no one's had to look at this, so they haven't been, until maybe the last 10 years or so. And then it's been seen as an opportunity. And the opportunity is potentially for island nations, or nations that don't have a reasonable continental shelf with shallow water to put it in, are probably some of the key areas for this type of technology, rather than being, the big power driver for, say, the UK. We've got a lot more we can develop in the near shore area, because the further away you are as well, the harder it is for your O&M logistics. And the further away you are, operation and maintenance logistics, the further away you are, you then have to maybe look at going to DC instead of AC systems, and DC converter stations are very expensive, because you can't, over about 100 kilometres, you can't really transmit with AC. The power losses are too high, so you have to go down a DC route. So I think it's playing catch up. I mean, the fixed offshore wind, you go back, it was getting very heavily subsidised. It's until quite recently, because it wasn't economic either. Now it's getting to the scale where it is becoming almost standalone. Same with the onshore. There was a big hoo-ha when onshore had the subsidy removed. How will we ever put another wind farm out? Well, the industry's managed to, but it's had to get the technology to that level to get the investment to do it. And the investment all comes from the big banks and the pension funds and venture capitalists. It's the power companies themselves aren't putting a lot of money into developing these. There's a lot of money coming in around that. A lot of our business is actually the due diligence with asset transfers. You'd be amazed how much wind developments transfer and ownership before the first bit of steel's melted to form the tower. It's an incredible amount of movement with just different funds and investment there, because they need to see that return on their money. This hasn't been there. And as an example, if Cowell hadn't have got theirs out last September, they'd have missed the ROCs funding. ROCs is £300 per megawatt hour. They'll get that. If they produce more than that, fine, they don't get subsidy. If they produce a value less than the strike, they'll get that £300 for every megawatt they generate. So that's a really high subsidy. Moray is out there at less than 50. It was bid and won at less than £50 per megawatt hour. And if the electricity price they're getting is higher than that, they get no subsidy. It's only if it drops beneath that, and that's actually almost in a really good position for the taxpayer, us. But we don't have that level of knowledge of these systems yet, and demonstrating they actually work. We'll come to that. For the banks and everyone else to invest heavily in it, and they're going to be more expensive. So if they're more expensive compared to what we can do in shallow water, they're not going to get ahead without proving that and taking it to other areas of the world where it is required. And Japan's a massive one for that. They want rid of nuclear. Just after Fukushima, they're moving and they're one of the key areas. Them and Taiwan are pushing hard on this as well. But again, it's demonstrators, because they've got to get to the stage. They can't put all their eggs in one basket without the proof that they're working. I don't know if I've really answered your question. I've gone round in a few different things. So if we think about what some of the market is, I know this is a 2017 report, but that's still the most recent one that the Crown Estate have issued. So December 2016, but it was issued in 2017. It hasn't been updated as yet. But at that point, I think it was interesting to note we had just over 5 gigawatts operating across almost 1,500 turbines. And what was in development at that point was almost doubling that in size, and not far off halving the number of turbines. So that talks back to the growth in the size of turbines as well. So we're getting more efficient because we're putting less infrastructure out there, but it's much bigger and more efficient. It'll be a lot more expensive to buy an 8 megawatt turbine than it would be to buy, a 4 megawatt turbine. But it's probably not more expensive than buying 2 of them. When you then start looking at the construction of 2 towers, 2 foundations, 2 sets of blades, etc. Hopefully you can see it becomes a lot more efficient to go bigger than to go with multiples. And that reduces the levelized cost of energy, and that's what everything's based on. That's when the subsidies are based on. When people are bidding, they're trying to work out that levelized cost of energy. That's the metric across all of the renewable market, really, is what is effectively the equivalent price to generate power compared to anything else. And that's what's used to identify the winners for the licensing rounds. Something that you might not be aware of, because we're very good in the press of belittling our credentials sometimes. We're actually the world's biggest offshore wind market. The subsidies that have gone into this, we all pay for it, but actually has been absolutely massive. We will be overtaken in the near future by China. It's got the mass and the desire and the fund to do that. But at the minute, we actually are the market leaders, and that's why the developers have been here for the floating wind as well, because this has been the biggest market, and it's been the biggest market because the government's looked to divert. The government of whichever colours over the last number of years have looked to diversify the energy market in the UK, and that means over a third of offshore wind's developed in the UK sector. So that's, again, if you're looking at careers in renewables, it just gives you a bit of confidence. There's a lot of stuff going on here. And what's been the thing that's really been hit by that? It's been the coal generation. This is a live website you can go onto. I took this off of it just the other day there. And you can see at that point in time, UK's demand was about 35 gigawatts. And coal was a very, very small contribution compared to what it would have been in the past. So that was one of the key things to try and achieve, Paris objectives and Kyoto before that, to try and reduce the emissions from coal. And that's been done quite massively. We've also got quite a strong contribution from nuclear, then the combined cycle gas, as well as also the dominant one just now. But you can see where wind was on that particular time and that particular day. It's becoming quite a massive part of our energy mix, for sure. So let's say you can go into that anytime. It's just keep that one as a live tracker of what's going on. So we talk about it's quite a dominant part of, the UK is a dominant part of the offshore wind market. And then our power generation's also got, wind's quite a dominant part of that now. As high as nuclear pretty much, and pretty much there's a number of times now where we've had the UK sort of coal free, haven't we? See, there's big press announcements about that. But even when we do have coal, it's a very small contribution to the overall mix now. And also the big bias over the years was a dash for gas, and as wind comes up, it might offset some of that too. If we look at the wider offshore sort of market, there's about 16 gig, so there's about 5 gigawatts in 2016 already in the UK. Across Europe as a whole, it's about 16 at the time. So you can see we're quite a large, about a third of the UK's contribution as well, and absolutely dominated across these areas by fixed offshore wind. Okay. But I've said earlier, the bulk of the resource is in deeper water, and that will be if we try and push it. I mean, 4,000 gigawatts, that's brilliant, yeah, but UK's only needing 36. You add up all of Europe altogether, that's more we could potentially ever develop, but it's not all blowing at the same time in the same place, Maybe having some deep water west of Shetland turbines helps to balance out for when it's quieter in the southern North Sea, where we've got a lot of the existing turbines. So there's a bit of a balance there. But the fact remains that most of this is going to be into deeper water. Areas like Norway, they've also, why have Statoil or Equinor now? Why have they been pioneering some of this? They don't really have much shallow water on the western seaboard. It goes deep very quick, so floating becomes an issue for them. Hawaii there's an area, Hawaii would like to have floating wind, but on the other side, it's a very large strategic point for their navy, and it does interfere from that regard. So there's whether they'll ever get that going or not. But the western seaboard of America goes very quickly into deep water as well. So there's developers based out in San Francisco looking to develop the turbines as well, floating turbines, to address that market. Obviously, fixed onshore wind, the States is starting to take off itself now on that side, with what's happening offshore New York. We recently hosted in the UK, in Aberdeen here actually, we hosted New Jersey, Virginia, Massachusetts and New York state delegations looking to learn from what we've done on offshore wind here and take that across to America.
So just relate to that point, I know offshore Europe's on again in September.
Yeah.
Is that going towards this technology as well? I would think.
Yeah, I would be a little bit surprised if it was, to be fair. The real conference to be aware of is All Energy down in Glasgow in May. That will have, again, it's normal. I expect that will have a forum there for floating wind again as well. But that's pretty much the renewable conference. I'd be surprised to see a massive amount, but I could be wrong. There is a renewable section within the programme this time, but I don't know. I've not looked at it in enough depth actually. Worth looking up the programme. But All Energy is the big renewable conference in Scotland, and that's in May down in Glasgow, mid-May. By all means, go down, see our stand down there as well. We've got a team of about 250, 300 people in Glasgow working on renewables, so we'll have our stand down at All Energy for sure. So it's a bit of the idea. So the wind market and where it is and where our position is within that. So what's the potential looking forward? So this is all driven sort of by the water depth, yeah. And what we can see is the potential. This is so BVG Associates. They're a consultancy in this space, and they did a study on behalf of what's been published under windeurope.org. As you can see there, these are all live, so you can go and get all these reports. So nothing I'm putting up that's sort of all secret squirrel. You can go and find this stuff. You can see monopiles. Their feeling is that's where we can get to with it, but it becomes a bit self-limiting. There's not much more of an upside beyond what we know we can do with it. There's not, and reducing costs is maybe not a great upside for the additional that we can do. If we do nothing, so baseline, so if we do nothing, leave technology where it is, and the upside is that we can continue to invest, continue to innovate and improve on what we do is where we could get to. You can see jacket bases have got, there's a good potential for growth there on an upside, but the real area for fantastic growth on this is, again, if the industry can sort of prove the floating turbines and take them forward, then there's a massive scope for growth within Europe on that. And as I say, there's other regions of the world where this is pretty good technology for them as well. If we look at it just that global perspective, taking it away just from Europe, if we actually, this is a map of sort of wind speed. Yeah, we don't have the blue bits on the open ocean just because it's not in the measurements there, but the sort of darker the colour, the sort of the higher the average wind speeds that we have, and you can see there around a number of the big population centres that we have. You know, we start to see those higher wind speeds, yeah, and you can see across some of these island communities as well. We've got reasonably high wind speeds in there, so there's definitely the market potential to put offshore and floating wind in a lot of areas around the globe where it hasn't been stepped out to. You know, some areas you can see there's a lot less wind resource here. Is it going to be economic? But definitely to hear, you know, again, high, strong wind resources. How do we work with them? And if you map onto that a little bit about where the population hubs are, which is in green, and then, you know, we're not really a big population hub up in Northern Europe, but it's actually quite a strategic area because it's somewhere that's investing heavily in it. And then we've got the island communities, and you can see they match up pretty well with where the wind resources were. So that gives us a good opportunity there to develop and take forward some of this technology. So just to go back over what some of the technology is. Yeah, so floating versus fixed bottom. So FOW, floating offshore wind, okay, as opposed to fixed offshore wind. So it's not, we don't think it's that different. Yeah, it's the same turbines, same towers I have to work on. The bits that aren't are pretty much going to be directly transferable, we think, from the marine energy sector and the oil and gas sector. So we don't think there's a lot of changes necessarily needed. So what we've got here is our onshore substation. We've got the cabling running offshore, so we've got all the same permitting, the consents, the seabed interaction with our cables. So that's all standard. Then we have an offshore substation, because all of these areas are going to come back via a substation somewhere where we can sort of rectify and convert the voltage, etc., for longer transmission. And these are just probably our standard 132 kVs here, back to our offshore substation. The offshore substations, they're much bigger structures than a floating wind turbine. They may still be jackets even into deeper water, but again, they would fit on some of our floating production facilities like FPSOs. So they could be, so in really deep water, they could be floating again as well. But the offshore substation, the technology on that already exists. It's either going to be same as we have for fixed offshore wind on a jacket, or it'll go into floating. So there's nothing new there, but we do have our dynamic cable, and again, that's an extension of what we do in oil and gas. Again, dynamic cables back onto seabed, and then our turbine, and it's all known technology here, then known technology down here from another industry. So the wind and wave and the climate engineering, well known. Cable jointing, we know about that. Soil investigations, we do that. Cable and barrel method, we do that. The infrastructure, so it's all well known. And as I say, how to access things that are floating, offshore substations, and the wind turbine, they all come from oil and gas or fixed offshore wind as it is. And the big hope, what we can do, this is an area we'll come back to on floating wind, is avoid some really large and expensive and unique construction vessels. Because at the minute, and you might have seen a few on some of the earlier slides, that to go and put out fixed offshore wind, we need some pretty large and specialised vessels to go and do that. Floating potentially allows us to do that in the harbour and not require these vessels, depending on what we're looking at, and that's something we'll touch on. So how do we get to floating? Well, it'd be interesting to look at how we got to floating from oil and gas. Originally, we started everything connected to the seabed as well. And then we went into deeper and deeper water and completely different styles of hulls and vessels. And we started in 1975 with only one floating. So we've talked about it at the minute. So oil and gas have been developed for decades and decades offshore. You know, the Gulf of Mexico go back 100 years, you know. But never went floating until 1975. It's a bit like that fixed versus why we're not using the floating yet, how we will get there. There's a bit of that demand in improving the technology. So, you know, when we compiled this chart, that's our old logo just there actually, but we went into Offshore magazine, that link's there so I can get the poster. So when we compiled this in about 2016, there was 330 floating. So you can see a massive growth of floating systems. And I think it's a similar thing we're at now with the wind. We're at the point where is it economic to keep it stuck on the seabed, or can we go to deeper water and float? And is that what we're going to do? Or in some areas of the world we just didn't have an option, we couldn't develop. You know, West Africa, we couldn't develop that. We went further offshore at all, without, you know, some significantly deep projects there. We couldn't have done that without going floating. So it really opened up new areas and new markets, and that will be the same with floating wind. So we can follow that sort of legacy and all those different, I'm not going through all the different types of hulls are, but you see there's massive different ones, but there's a lot of similarities when it comes to the wind sector. You know, we're putting things in the water that need to be corrosion resistant. It's exactly the same on each side. There's the naval architecture and structural engineering for the hulls, exactly the same on each side. We have to anchor them to the seabed and understand the seabed and the geotechnics. It's exactly the same. You know, it's saying there's not a lot of difference there. You know, we have to forecast the waves, we need to understand the wind resource there. It's all stuff that's been important for us across the globe when we've done offshore, you know, energy for the oil and gas sector. It's not any different. So there's still things we need to look at and demonstrate. There's enough knowledge there you can start to bring things across. But you have to do it right, and it's not. So you can say, why do we need to do the demonstrators? If you go back to the very early doors, some of the early fixed offshore wind, those big piles that go into seabed and the bit that comes onto the top, they get grouted together. And that was taken from grouting work that was done in oil and gas for piles that were a fraction of the size, a tenth of the diameter. And lo and behold, they started to crack and fail. So the idea was right, but the codes and the standards and the specifications weren't quite reasonable for the step change in the technology. And there was big problems and a lot of insurance claims for fixed offshore wind because of the grouted connections. So they had to evolve that. So they took the knowledge, but it had to be developed. And it'll be the same here. The knowledge is there, but you do have to take it across. And actually scaling down in this regard is where some of the challenges are for us. You know, the hull's going to respond a bit differently. It's a smaller hull. A big hull, it doesn't matter what moorings you hang off it, it dominates the movement. You go to a small hull, then the like cam buoys we have, look at small buoy structures where we use, they can be dominated by the mooring loads. So we have to be, we know we can transfer knowledge, but we also have to be aware the areas we have to research and push a bit further as well. So I mentioned there's a lot of different styles out there. This is just some of them. So there's the floating power plant with the combined wave energy converters we have here. We've got principal power, three-legged semi-submersible. So beneath there, there's big pontoons that give it the buoyancy to float. Again, that's a steel hull. We've got Ideol here. Ideol are almost like a barge, big square barge, and it's a concrete hull. You've got the Statoil one we've talked about. To date, Statoils have been steel, but they're looking at also the option to do them as concrete. You've got a lattice structure here, which this is an interesting one with Hexagon. 2 turbines on the one foundation. Yeah. That was a way to try and, how do we reduce costs? Do we have 2 hulls or have 1 hull? But you've got a limitation there. You think, you know, the diameter of these blades could be up to 180 metres, some of the new turbines out there. So how big does that structure need to become? Does the hull become too big? Is it cheaper having 2? We never really got the chance to find out, because unfortunately their venture in the UK, Dunray Tri, went into administration, but the parent company's bought all the IP back again on where they're going with that. So, hi. Sure.
I was wondering, with the decommissioning of old platforms, can the foundations be adapted for wind turbine foundations instead of removing everything and taking them back? That's one question. generally in the
Mm.
UK, considering the fact that when the Hinkley power station,
Mm.
nuclear power station is completed, it will really supply like massively,
Mm.
you know, and even currently with the level
Mm.
of renewables we have, they are still subject to curtailment. So when
Mm.
the nuclear power plant starts working, will there really be much more research going on?
It's not going to cover all of the UK's needs. So to answer that second one, that still won't cover all of the UK's needs, and there's other equipment being decommissioned as well, and power plants that are going to be shut down. So we're still going to need that mix coming in as well. And Hinkley's could be a good long way away before that one's finished as well. We've got a team working on that from our offices down in Bristol and London. So yeah, I don't see that being the risk to the renewable side at all. And our energy needs may only increase. You know, if we start using less oil and gas for transportation, then that becomes an issue for us. We may even be, Leeds are looking to maybe see if they can go into a hydrogen economy. At the minute we can't just change everyone's cookers out to hydrogen gas or natural gas. You need to change the burner. The UK went through that, I don't know, before my time, 60s and 70s sometime, we changed from coal gas to natural gas, and every single burner and every appliance had to be changed for that. So I don't think we could go all the way to hydrogen, but we can start to blend hydrogen with natural gas. Now you've got to generate that hydrogen. Again, you generate that from electricity. I've got electric car to generate electricity for that. So I don't, so there's other things coming into that mix as well. I don't see an issue on from that side. The decommissioning, I think yes, you could use one of them to support a turbine, but on the footprint of an oil and gas platform, you're probably only going to get one turbine. Turbines need space between them. They're not big enough on the top to get multiple turbines. And the challenge is, when you take away the top side, you still leave the jacket. You've got drill cuttings and other things maybe within the leg. You maybe got damaging hydrocarbons and benzenes and carcinogens and that within the legs. It all need to be cleared out. And what you're doing at that point then is you're transferring a liability. That'll only be for one turbine, so it's not. And then you've got that whole decommissioning liability because someone's got to come and take that out again at the end of life. So there's not the economics because you need 100 turbines out there type of thing for a decent development, not the one. So that would just be a big issue. The potential is possibly as an offshore substation, but I don't think anyone in the clean energy space will really be wanting to take on it or get involved with decommissioning liability for an oil and gas platform. Particularly, a lot of these are on top of old wells that might, the idea is they should never leak, but the reason there's a liability there is if they do, the operator has to go back in and fix it. If that asset changes hand, then, well, you're the one that caused the problem. We're not going near it. So there's a big issue, I think, on that side. However, while we're decommissioning the Beatrice platform, we put lots of little mini turbines on there to help replace the diesel generation. So there's bits and bobs you can do, but it would never be something for a development in my mind, no. A number of different types of these here. This is a bit Style offshore, got something that looks a little bit similar to that, completely different mooring styles as well. Kincardine offshore wind. What's really interesting with Kincardine offshore wind is they're now owned by a Spanish infrastructure. Well, the principal driver behind that's a Spanish infrastructure company called Cobra, and they couldn't get enough people to farm in to help develop and design this new hull. They had an idea of a special hull. So with the semi-sub there, concrete barge, we've got what's called a spar here, very tall and deep. This was something that was a mix between the two. It could be up on the surface and then sink for transit and then sink down a bit more like a spar for operation. That's not what's actually out there. If you look closely to what's out there, it'll look identical to Principal Power because to get the subsidy, they had to get a turbine generating. The metric is you have to be producing electricity by the date that the expiry date on the subsidy. If you don't get it in by then, now they've got it in, they can put the other 6 out there and take their time. But they had to get one in there, so they've actually stuck in Principal Powers. So it's quite an interesting one, but they still want to go and do the rest of the development with their own ones. So, and it does on a sunny day, you'll see the yellow and the white, different colours shining back at you from offshore as well. So a heap of different technology, and I say nothing's been settled on yet. I think this one at the bottom right, I'm a little bit sceptical on myself. That's, yeah.
When you've got a non-symmetrical floor, like the principal power and stuff,
Yeah.
is it just the nacelle that the cage for like yaw control?
There,
Does the whole structure, or does the box structure weather rain for the waves on top, or how does that actually work?
yeah, so that's actually, you can have non-symmetrical floaters. That wouldn't be unusual.
So you don't let it balance.
But some of them, the drivers are, for some of them, they are wanting them to weather vane as well, and not necessarily to avoid completely on the nacelle, because you want the turbine into the wind. Your hull's going to be dominated by current and wave loading, so they may in different bits. You're still going to need that control. But the hexagon one for sure, that was very much turbine, and then there was a swivel there, and it would actually rotate around that point all the way around. So it's a bit of a, so again, that's part of the not quite settled technology. If you want to use a swivel, you want it to rotate, then you have to be able to have a means where you can allow electricity. The cable coming in then has to split into two different ones, and you need to have the ability to allow relative rotation between the two sides of that in that swivel stack and that electrical ring. And there's a limitation there for maybe high voltage systems having that high, in that swivel. So there's different. So again, that's one of the bits that's not settled as technology either, as people try and work their way through. Is it cheaper to try and do that, allow it to weather vane around, or should we just spread moor it, stop it from moving, and then have a simpler connection arrangement coming in? You just basically pull your cable in and plug it into your electrical board at the bottom of the tower. Simples, there's just different ways around it. So there's a whack of different styles there, but they sort of mirror quite well some of where we are in oil and gas, where we've got the semi-submersible style, which is very much this type of thing here. We've got the spar, which is a big long cylindrical deep hull. Well, there we go, we've got that. I should have updated that to Equinor, really, shouldn't I? Yeah. In there. And then you've got what's called a tension leg platform here, where you've got something with significant buoyancy, and it's held straight down onto the seabed with rigid tendons. And that's what SBM have on this system here. So you could, although it's a whole different sort of mix, they're actually sort of trending along similar technology ideas, but with their own little nuances that we've seen before. So looking at some of the basic characteristics we have with the hulls as well. If we look at those sort of three generic types, so a spar's really deep draft. Yeah, I think so when I say draft, it's where the bottom of the keel is compared to the waterline. Okay, so the Equinor ones that were going out were about 75 metre draft. So actually, you've got to be in deep water for them. They'll not, you can't use them in 30, 40, 50 metres. And basically that's just a massive there's two things. That's a counterweight against the turbine, the tower and the turbine, because the nacelle's way above the waterline and it's got load on it, so it's a big counterweight to stop the thing moving. And also, the deeper you go with that, the less wave action you get as heave, moving your system up and down, because heave's generated really by the change of buoyancy. And if you've got something very long and slender, then you're putting the keel beneath the wave zone, and you're not really getting that same response at all. But it's very large draft, and that becomes a problem for its assembly. I'll have a picture of that later on. So at the minute, the big issue economics on that for install, but you could change that, come up with new vessels. That would sort of that would put us back in the same problem with some of the vessels that we need for fixed offshore wind. But it's very good motion-wise. It doesn't have a lot of motion because of the type of hull that it is. So it doesn't move a lot as the waves come round, which is quite good. And you've got just catenary moorings coming down onto seabed, so that's fine. You've got heaps of different options we could use there. So there's not a big issue with the soil sensitivity that we have, because we can design a mooring to suit. Something, a floater, a semi-sub or a barge on the surface, well, they ride the waves, so they do move quite a lot. Yeah, they bounce around a lot. And that's a big problem that could be a big problem, because all of our fixed offshore turbines, our onshore turbines, they're pretty much static, aren't they? So you're not putting a lot of extra loading onto the bearings and things like that. Once you've got something moving about, pitching and rotating, you're putting a lot of acceleration forces in there, particularly the further up. I mean, it's all going to be moving around the centre of rotation of the hull somewhere there, and you've got something, a massive lever arm away from that. The acceleration, the forces going into that are going to be quite significant. That's part of the demonstrations to prove we've got the bearings designed well, etc., the gearboxes, etc., so that things aren't going to fail. Again, it's good for the moorings, and because it's shallow draft, maybe we can use a crane on the quayside to lift the turbine on. But we don't need big, expensive offshore install, we just need tugs to take it out to site. There's the big difference, you know. And then we've got TLPs. TLPs are, as I say, it's a very high buoyancy structure, and it's inherently unstable. If either of these other two lost its moorings, they drift. That's what they do. Yeah, so not the biggest issue. It's still an issue. I mean, I was involved with the BP objected originally to Equinor's pilot high wind development, because the Forties pipeline, one of the major pipelines in the North Sea that comes across, it's about the 75 metre contour, exactly the same depth as this. So if this went off station, it could have pogoed into it actually. So BP, how they got round that objection, so we were involved with how much rock would you need to actually stop the turbine before it hit the pipeline and not damage the pipeline. And then that was quite an easy solution for Equinor to implement, because they're quite used to relocating bits of mountainside in Norway and putting it in the water to protect things. So that's what they did, and protected the pipeline. But other than that, it's not not a big issue. It's just you just got to get it back again, I guess, before it hits something. A TLP, on the other matter, is inherently unstable. If you lose those moorings holding it down, it'll invert, it'll turn over. There's a really big, the big issue with that happening. I think it was the Thunder Horse platform in the Gulf of Mexico, and the Hurricane lost its moorings, turned over, and all of the tens of thousands of tons of top-size equipment and process went straight to the seabed. It's now one of the world's biggest artificial reefs. That's what it is. It's gone. It was never coming back. So getting them to site can be a bit of a challenge, but they also have very limited motion once they're out there, because they're rigidly held to the seabed. So the mooring systems as well, so pretty well defined, but again there's sort of different options there depending on what we're looking at. We've got taut, which is very much said that's for the detention leg platforms, that's tendons rigidly into the seabed, and you need to have really good ground conditions for that. Or we can have semi-taut or catenary. Semi-taut give good control on excursion envelopes of a vessel on the surface, and tend to use them maybe with fibre ropes. But they've got some challenges of their own, and again, you're coming into the seabed something at an angle, so you need piles in the seabed. Can't really use an anchor. Anchors don't like any vertical load, so you've got different issues with your seabed. So maybe it's a catenary. A catenary tends to allow more excursion on something, because it holds a vessel in place. Basically, as the vessel moves off, you pick up more catenary from the seabed, so you get more restraining force, whereas this is always tight, as it were. So you get bigger movements with something like that. But most things are probably going to be that for the foreseeable. It's an easy thing to anchor to the seabed, a lot easier to hook up, because it's not pulling something ramrod tight to try and hook it up either. So most of the systems out there are, at the minute, demonstrated are all catenary systems. An issue with them all, and this won't go away, is working with the fishermen as well, because turbines are going to be 750, 1,000 metres apart, say. And if you start putting a big array of them out, and the moorings coming off them are going to have a spread maybe 500 metres in radius, if not more. Oil and gas rigs are about 1,500 metres, almost a mile away from the platform where the anchor is. You start putting a whole area, dozens of these out there, you're eating up a lot of the seabed, and you're going to run into. So at the minute, you've got the societal impacts on shore for planning. What you have is other industries having concerns once we go and put these things on offshore in greater scale. So you've got the turbine spacing, and that's going to push us apart, and then you've got the mooring footprint around that. 'Cause you also can't come in, any fishing net coming around here is going to get lost on the nets. The chains will just take them away. So what is the mooring types we've got as well? There's a whole range of things there. There's chain, there's wire, and synthetic rope. They depend on the seabed types, for sure, the water depth we're in, and what sort of hull type we have. As we go into deeper water, we'll maybe try and use maybe heavyweight ground chain on the seabed. Try and get chain on the seabed where you can, just because you can get, with synthetics and wire, you can get abrasion as grit and that gets into the wires. And east of Wales, we try and use chain, but maybe instead of having chain, which is nice and cheap all the way through the water column, maybe we'll change it to wire so we can reduce the weight coming in at the top. But if we make the mooring system lighter, it's not going to have the same sort of rigidity to stop movement of the hulls. Okay, and something else I was saying earlier, as these are relatively small hulls, the mooring, if they're heavy, can then have an impact on actually how that system performs as well. So the whole sort of closed cycle there. But generally, I think it's going to be chain and wire for the time being that we have. But again, each solution is going to be slightly different. Definitely, as we go deeper, it'll have a big impact on it as well.
What are the major differences between ordinary semi-tart and tart? Tension legs, is it just the tension, or?
Oh, I mean, tension leg, they're vertical legs straight down into the seabed. Yeah, they've got massive load in them, and they will actually not be any of these. Or maybe they might be wire for floating wind, but for fixed platforms, it's actually rigid steel bar, effectively. There's massive load because you go out with your vessel and you pump water out your hull, and it floats up, and there's massive load there. So that's direct load straight into the seabed. So it's how you drill into the seabed and you grouted anchors back into sea. So you're very long depth into the seabed as well to get the friction, stop it pulling out. Semi-taut's going to need piling because you've got you can't use an anchor generally if you've got a horizontal load in, a vertical load in there. You can see they've got that there. We use these quite a bit for some of the deep water systems though. We can use, it's very hard to maybe control our excursion envelope with a catenary and keep the weight down for using synthetic rope. So we can use synthetic rope and some of it stretched to come up with a semi-taut. So we've got something that's, it's almost straight lines. It's not got much sag in the catenary, but they're not vertically straight down into the seabed. And then a catenary is as it looks, it comes down, and it's all the movement of that catenary is what holds back the load response. Okay. So one of the big things we've got to look at as well, and this is where you start looking at what's the differentiators between this. If we're in oil and gas, we go and put one thing out there at a time generally, yeah? One platform, one floater. So we come up with the moorings for that one floater. If we're putting out a whole array of a development here, now, as opposed to just a demonstrator, if we're putting out a whole bunch of turbines, are we going to moor them all individually? Or can we, so if say we put 3 moorings on each turbine, then there's 3 anchors for each turbine as well. So there's a lot of infrastructure down there. Can we actually go down and share an anchor? Say the squares of the anchors. Can we actually share the anchors between adjacent turbines? Could we do that? And that's something that's been pushed out there quite a lot in industry. And now I believe that's what Statoil are about to do in Tampen. As part of that demonstrator in the Norwegian sector, is look at sharing anchors. There's pluses and minuses for that. If you lose an anchor, you've not just upset one turbine, you've got a knock on throughout the system. Also, how do you hook it up? Could be a bit more challenging maybe, but there's a way to maybe bring down some cost for floating wind, not to have individual anchors everywhere. And another one I've seen proposed, but it's a bit more of a challenge, is why not actually have a series of turbines moored to each other and only the outer ones anchored to the seabed? Now, there's a challenge there, because what if this one's needs some real significant maintenance and it needs to be taken back to shore? You can't really disconnect from this, so you've got to have a think about what happens if you've got to do operational work in the future. How's that going to impact your system? But that's certainly something that's getting a bit of traction at the minute. To say with Statoil Tampen, this is now looking at this our next area they're putting out there and thinking, what can we do differently? And that's definitely one of the aspects for that. That's quite a positive change there. Looking at, so again, that's something that we're having to think differently from anything else that goes out there, because they only go out in 1s or 2s. This is something where you're going to put out dozens of them. How do we make that more efficient? how can we improve on the technology. So that's one interesting one at the minute for sure. There's something else in my mind about moorings. If it comes back to me, I will come back on that. Okay. So what's some of the challenges that we have with the systems as well? There's, as I said, this is moving around now. It's bouncing around in the environment. So we're going to get fatigue. Fatigue's just basically cycling motion on something. You repeat bending it. A bit like, simplistically, you get a paper clip and you start bending it back and forward. Eventually it breaks, yeah? Same thing happens with steel, so happens with cables. And what you can see here is, steel armours in there. And then we've got the copper conductor. So this would be an AC cable, 3 cores within there. The blue stuff's just fillers. That little one there, that's a little tube for a fibre optic for comms going out as well. So you try and do more than one thing with the cable. Use it for your communications to control infrastructure, as well as having the power. That's the cores there, and then you've got insulation materials around outside, and there's got copper screening there as well to try and limit interference between them. But we're bending them back and forward. Yeah. Now we do have cables going back up into oil and gas platforms, but they're not big 66 kV or 33 kV power cables. They're a lot smaller, so the bigger the cable becomes, the higher the stresses within that as you bend it, so the quicker the fatigue. So that's something that industry's having to address and look at as well. So it's a step out of technology. So, and whether it's going to be in DC cables, DC would be one big single conductor in the middle. That's in a way that's even worse than having 3 smaller ones, that we have there. So how do we actually perform and demonstrate the fatigue performance of them? So that's something industry's pushing forward with. Something I touched on earlier is the loadings on the turbine. Because the hull's moving, we've got accelerations and motions that are being forced into the structure. So the blades have got extra loadings on them they wouldn't have seen again, some cyclic fatigue loadings at their connections. And we've got the bearing loadings within the turbines and the gearbox as well. They were used to one set of thrust loadings. Now that thrust loading's got a whole 3D sort of component to it because of the hulls. It's pitching, it's rotating, it's moving in all 6 degrees of freedom. That's putting more load onto the system. What does that mean for wear and damage as well? So maybe it's not going to exceed extreme loading requirements, but are we going to have to, these demonstrators tend to go out for a year, say, yeah, we've been off Portugal in big ways for a year, it works perfectly. Your pension fund doesn't want to go into it unless it knows it's going to be there for 20 years or whatever, So there's a bit of demonstration of knowledge of that as well that's been developed. How we actually model these, and I touched on this as well, and I'll come to it a bit later, is how we pull together aeroelastic and hydrodynamic modelling. And as I say, the International Energy Authority's got a global programme looking at some of that as well. And so many universities got little research things going on this as well at the minute. And it's smaller hulls than we see in oil and gas, so they are going to be impacted by the weight of the mooring and the cables. Generally in the big oil and gas ones, you can work out your motion response for the hull, fine, that's it, you've got it. And when you hit it, so once you know that response characteristic for a given wave, you can put that into model and say the vessel's going to do this, and the moorings and the risers you design knowing they've got something doing this on the top. This is a little bit different. This is, because it's smaller hulls, you can't really work it out in isolation from the mooring and the risers on them. And it's that combined modelling again, and the coupled assessment of that makes it a lot more complicated. I think also there's how do we move some of the active control systems as well, to help with efficiency, to avoid damage in high wind scenarios. We know fixed wind can use active control systems. How do you marry that into something that's also got motions and accelerations coming from the hull? It's completely different algorithms and code required for that, and that's another area being developed just now. So that's another, there's an opportunity there for the people that develop that, but it's a challenge of how do we actually maximise the performance of these turbines as we put them out. How do we install these? So I was saying before, we've got to use some big specialist vessels for fixed offshore wind. Well, nothing like this one here. This is on a different scale altogether. I can't remember how much the Saipem 7000 can lift, but it would be well over 10,000 tons in a single go if it needed to. Complete overkill for this. But this was for Statoil Equinor now on their pilot development, because these turbines are 75 metres deep, they've got to be off from deep water. So you need to get a crane out there that can actually land the turbine onto that. And the big driver was actually having a crane with a hook height, what can reach up over 100 metres on a vessel, to drop this in place. That was their challenge at the time. So they've used a vessel, it must be, it could easily be $300,000-400,000 a day on hire to install. That's never going to be economic for a massive array. So Statoil have been running, and they've gone out to industry and looking for ideas for, can they just get something that can clamp on at the waterline and sort of carry this out and drop it in place? But they'll have to develop a new vessel if they stay with the spar concept. But the other ones that float, they can come into shore. In fact, you can actually see there, this one is in a harbour. Yeah. So if you've got something with shallow draft, you can bring it into harbour. You can integrate everything using shore-based cranes. You know, you're nowhere close to those sort of prices. And you know what? I'm probably undershooting the price of a lift vessel like that. You know, this is the things we use to lift oil and gas platforms in and out of position. It's overkill for something like this. How do we do the maintenance, overhaul and redeployment of these when they're so far offshore as well? For fixed wind, we've got special vessels that will go out there and they'll jack themselves up out of the water to get their crane height, and they can go and change out the turbine if they have to. Are we going to have to come back with this to change out a turbine on one of the Statoil ones? Is it going to be more economical to actually tow them all to shore if we can, and work on them inshore? How are we going to work that? So again, that's where we're trying to understand the costs and how we do that, and what technology we need. And there really is a real difference here, and I think something BIFAB are a bit caught out with. It's for these large-scale fabrications, we're not set up with a mindset that it's like a car production line, or it's, you know, cans of beans coming off a production line, but that's that's all right. But that's exactly what it needs to be. If we're going to cut a hull out of a shipyard for one of these and get a hull every 6 months, that's not going to help. You only start getting a return on your investment once you start generating electricity, and you're putting all this money into the procurement and the fabrication. You want that to go as quick as possible. So fixed onshore wind, certainly with monopiles, onto a winner there, you can really start getting them. You know, once you start your offshore works, it's quite quick. You're not really waiting on fabrication of all the monopiles, because they're relatively quick and you can get them coming along. How do we get to a stage with offshore wind? Which technology is going to allow us to build a lot of things in parallel, or have multiple sites in an area? We're not going to be able to take over all of, say, Europe's dockyards to get this going for. How can we do that? And that's an area there's a lot of studies on, good stuff with the Carbon Trust as well, if you want to read up more on that. But how do we change our mentalities and our capabilities to actually look at it as a production line, rather than sort of, build a vessel, it's a one-off vessel. It's not. We're going to have to build a lot of these, otherwise it's not going to be particularly economic. And there's another one. I mentioned Tampen. Tampen's actually, this isn't Tampen, but it's a similar idea. Tampen is actually Equinor looking to generate power to help them produce oil and gas. It's absolutely what they're looking at on that one. It's to try and work with a Snorra platform and another platform, I forget which one it is, to see about generating electrical power offshore, so they don't need to run gas turbines offshore or have diesel generators, or at least they can throttle back on what they do with them. So they're looking at an array development with shared anchors, but it's not to produce electricity for the grid, it's to produce electricity to actually enable them to continue producing at a lower environmental cost oil and gas. We still need the oil and gas for, we're all wearing oil and gas, we've all got equipment, so it's not going away, but we can decarbonise how we produce it, and then go for, electrical hydrogen carbon and decarbonise that way, but still things that we're stuck with at the minute until technology advances. So it's one way of doing that. So they're looking at that, and effectively what it is, we've got an example here is this is a floating production storage and offloads. So basically, a big hull with process on top, basically a refinery sitting on top, moorings down to seabed and all the riser system. And what we'll have is a number of wind turbines that have a cable back up to it to transfer the power from that across. And there's a lot of traction on this. I mean, Norway, sort of ahead of the game as always in a way. They're looking at that because a lot of their recent offshore infrastructure was designed to be powered from shore, fitted for but not actually implemented. So they never ran a cable back to shore. Now they're thinking, well, it's a long way back to shore. What if we did this instead? Because we've set ourselves up for electrification. It's certainly a way forward, and there's a number of assets in the UK sector that are becoming gas deficient. So as the life goes on, they may be producing less gas, and maybe not enough gas that they've been reliant on to power the electrical requirements offshore. So they then have to start putting in new lines, bring gas from somewhere else, or start bringing in diesel to run diesel generators and that type of thing. So this is something, and the Oil and Gas Technology Centre are trying to fund some studies looking at this just now as well. So there's a whole thing about bringing power to the grid, but it's thinking laterally, what other opportunities are there for it? And that was one that's come up relatively in the last year or so. It's quite an interesting one. So it's working hand in hand with sort of clean and dirty, as it were. You know, the sort of energies coming together and trying to work to move forward. So I don't think we've quite worked out all the things we'll do with offshore wind or offshore renewables as a whole yet. So what's some of the challenges that we have with this as well? So we're trying to model it. So it's environmental modelling. So we need to be able to come up with the statistics for the mid-ocean characteristics. So, you know, what is the wind loading, what's the current loading, what's the wave loading that's in there. So, because as well as the wave in the air, we've also got the currents moving subsurface as well. So we need to know that. We need aerodynamic specialists, because it's a turbine blades here coming in, and understanding the CFDs, the computational fluid dynamics as well, for the wakes coming off the back. So how can we lay out our field? So that comes down to knowing, you know, what the resource is, its general direction, and how we're going to space out our turbines not to have overlaps of wakes and losing power. You want to get the maximum power from each turbine that we can. We've got the naval architecture, because we've got a hull in the water, we've got moorings, we've got dynamic cables, so riser engineering as well. We've got geotechnics on the seabed, and sort of structural engineers. So it's quite a multidiscipline thing to work forward with. Yeah, there's a lot, and we need to be able to assess each of these different bits in turn. For those of you not familiar with things, I guess, used to seeing things bob up and down in water, but what we get is the linear motions are sort of surge in and out of the wave, sway. A wave hits something, it doesn't just move it forward and back, it moves to side as well. So that's the sway. You heave up and down the way. Then you've got your roll and your pitch. You sort of understand that as well, and then yaw, because it will twist into with the wave coming past as well. Whether it's cylindrical or non-symmetrical structure, we get all of these aspects will come into that. That's the type of movements that you're seeing there. So we need to be able to capture that, and as I said, there's some real challenges around that. So, you know, the different companies, ourselves are one of them, are coming up with new tools. So we've extended our FlexCom tool with FlexCom Wind. It now integrates with a tool called FAST, developed by NREL, and FAST is an aerodynamic package. We've got a market-leading hydrodynamic package for hulls, moorings and cables, and you bring together the turbine loading, the wind loading, the hydrodynamics, the hull response, all of that together into one. So sometimes easier to see than to...
Welcome to FlexCom Wind, the new floating wind turbine modelling software developed by Wood Group's Digital Solutions team. Although traditionally used in offshore oil and gas, FlexCom is a versatile application which is also used extensively in the renewable energy sector. In response to the growing interest in offshore wind, Wood Group established a technical advisory group from industry, and feedback received has been used to guide the development of FlexCom Wind. First launched in April 2017, further, more advanced versions of the software will be developed over time. A state-of-the-art aerodynamic model is delivered via a fully integrated coupling with the industry-recognized FAST software. FlexCom's renowned finite element formulation facilitates highly detailed structural analysis of subsea components, such as mooring lines and dynamic cables. A superb user experience is delivered by Flexcom's modern interface, which includes a seamless integration with the FAST software. The user interacts directly with Flexcom, not FAST. A comprehensive hydrodynamic model of the floating structure is provided, including high and low frequency wave forces and frequency-dependent added mass and radiation damping. The software has been validated using test cases sourced from the international benchmark project OC4. Flexcom Wind has a highly intuitive, easy-to-use interface. Inputs are defined in engineering terms and logically grouped into familiar components, such as blade, tower, floater, and so on. The program allows detailed models to be created quickly and easily, allowing the user to concentrate on the engineering design. The automated post-processing feature presents the designer with key information, such as power generation, platform motions, and stresses in dynamic cables and mooring lines. Flexcom Wind comes at an affordable cost structure and has very flexible licensing options, ensuring that the product is readily accessible to all device designers, including fledgling startups and early-stage concept developers.
One thing I was going to stop and show, so we've got the moorings coming down here, okay, so they're a much wider footprint than the cable. You notice the cable's not just coming straight down onto the seabed, yeah? That's because the motions that we can get offshore can be quite significant. In the North Sea, the 100-year wave could be about 30 metres peak to trough, so pretty big. And we might be in 80 metres of water or 90 metres, say it's 90 metres of water, that's a third of the water depth disappears. Comes back on again, effectively. So you can imagine something floating's got massive movement there. If we just came down nicely onto the seabed with that cable, what we'd find was overbend, we'd have a lot of problems. We'd buckle it, we'd damage it at that point in the seabed. So what we do is we decouple it from the seabed, we try and basically effectively make it into a bit of a spring and take away that direct movement from the vessel from happening at that seabed interface. And we do that by putting on basically a bunch of buoyancy floats along there just to form a bit of a hog bend there. It could be a mid-water arch instead. There's different ways we can do it, but by doing that, a lot of the movement gets taken up in this area here, and it's a lot more static coming down. It still moves, but we're not going to overbend and damage it in the same way. And that's direct knowledge transfer again from other industry. So I don't think there's much longer on this. I won't subject
The
it
software
too
is suitable for all stages of device design, from conceptual prototypes right through to full-scale versions. User feedback is an essential part of our software development process. We would welcome the opportunity to introduce you to Flexcom Wind and offer you a free trial version to facilitate your own personal evaluation. Insight gained from experienced engineers will help to ensure that our product is fully tailored to offshore wind industry requirements. Thank you for watching.
from when we were still called Wood Group, so there you go. So I thought I'd just show that, it sort of talks through some of the different parts of the design, and I guess when we're talking about moorings and cables and what's there, I'll get a wee bit more of an animation of it to see how that comes through. So it's quite a, so they're very much, it's an engineered solution that we have to work to there. Maybe that gives a bit of a taste of some of the complexity, but it's all these different disciplines coming together, being able to work together and having, you know, some of that's tied in obviously within that software. Just as an example, this is a relatively small wave going past. I think it was a 4 metre wave. When I analysed this one, what we have here is the rotation of the vessel, and that was a 4-degree movement of the vessel from here to here was sort of 4, so it's +4 -2 in this particular one, because it had a little bit of a pushback because the aerodynamics on it actually set it back a bit, about 2 degrees, and then it was sort of rotating back and forward around that position. So those rotations are going on. It leads to big variations in the loads in the mooring system. So for instance, as an example of some of the output that comes from the modelling of them. So being able to calculate that and understand that's going to allow us to understand the thrust loadings going into bearings, the loadings that we have to consider in the mooring system itself, the catenaries, the hull structure as well. You can see in that previous one we've shown some stress analysis within the structure as well, the colour coding that was happening. To understand the most highly loaded beams, can we actually reduce some of the sizing down? Do you have to make them bigger? that's a very nutshell. I'm not going to go and labour about modelling analysis. Not everyone here is going to come from an engineering background, on structural side or that. So, but just at a high level, just to try and introduce some of the complexities and the things that need to be looked at. So really, just to round off, and then there'll be time for questions, I guess, or an early lunch, whichever way you want to go. But I think this is an area of industry that's seen as to having some massive growth opportunity. It works in deep water. A lot of our resource is going to be in deeper water. There's countries that don't have shallow water to put these in. Yeah, so it's something that's going to help us help globally to meet our energy demands going forward. We need to get over this development phase, though, prove beyond the single demonstrators that we've had a number of them out there in different regions of the world. We're showing the first pilot array, it's been out there now. There's another one being developed now for Norway, others will follow on the back of that. They're going to help bring the cost down, that £300 per megawatt hour. It's never going to win any competitions at that, really. As that comes down, the cost of these things come down, they're going to become more attractive, and there's certainly some island communities I think that would be really interesting because there's thoughts of wave for them, there's thoughts of tidal. Well, actually the one that's most mature out of any of them at the minute really is floating wind, and if you've got something where you can keep your moving parts in the dry, it's got a real good potential, if there's a wind resource there, to actually outstrip tidal and wave developments in these. It's a real risk. I sit on Wave Energy Scotland's board, advisory board, and that's a real, we're really trying to get wave energy across the line, but there is a risk where we thought areas this could be really useful for could well be overtaken by floating wind actually. So, but yeah, I think it's a great thing to be involved in. Actually, I'm really enjoying the work we do in that, and it's certainly the future from what I can see. So, anyway, that was a bit of a high-level whirlwind of what is floating wind, some of the challenges, some of the technologies, some of the resource that's out there. I'm happy to take any questions. The last, I guess we've got 15 minutes.
Regarding the power cable, so when we have a wind farm, each wind turbine connected to another wind turbine before it's connected to nearest substation, or just from one wind turbine connected through the nearest substation to achieve 132 kilowatt?
Yeah, I think it's a bit of a mix of the two, actually. There's some of them will be done in series, but then you might have different legs that then come back into the substation, so you're not putting everything at the risk of a single point of failure. That's a big issue if you've got a single point of failure. So there's a mix there, and it's sort of dependent on the size of the array and how far offshore, etc. it is as well, or how far from the substation you become.
So we've been told that since we have intermittent of energy sources from wind, so the electricity generated through wind turbine will be converted to DC voltage first, and then inverted to AC. But the question is, where we convert?
No, a lot of developments are AC.
DC.
AC. DC is for longer. The big driver for that is distance, as I understand.
Okay, so we have 132 kV for DC, or from wind turbine to.
If you're not far, depending in southern North Sea is not far from shore, and DC is very, very expensive on the converters, and there's only two main companies that do them as well. So you try to stay well. So that's a big issue. That was one of the issues for the further extension of Moray wind farm. Is does that become DC or not? So I'm not an electrical engineer; it's not my specialism, but I work with people who do, and the big issue is the cost. So if you can manage without DC, you tend to do that because you want to. I mean, AC is what you need for tying back into the grid. So you can't go DC and leave it all the way. You station both sides. Where that station would be, if you need it, and Germany have got they've got a very narrow linear offshore sector, so a lot of things far offshore, so they have to convert to DC. But you do that with an offshore platform. Same as you would for the you used to have an offshore platform anyway for if it was AC, you still need to rectify your voltages and the rest. So that would be an offshore platform. But for DC, you also have to have an onshore one to convert it back, which we do for the big power interconnectors to Europe and the rest as well. All right, well, hopefully I've given you something new there and you could understand most of what I said. So, all right, thank you.
Thank you so much.
Did I just stop that?
Just